thanks a lot for the invitation of this exciting workshop. I hope at some point we can actually go back to Sanya as well and see have workshops there as well. So this talk, let's first I want to set a little bit the perspective why we are interested in this stuff, asking these questions. And this really was, at least for some theoretical physicists, very interesting to observe these huge developments in machine learning, and in particular also to see things happening in other domains. One thing to mention here that I think is very impressive is to see somehow that a machine was able to discover moves that experts in a particular domain were not seeing for, have not come up with over centuries, or were discarding. And so I think this is a real, potential for something very deep to ask, namely, could we actually ask a similar question in physics? Namely, whether we could, get a similar type of discovery in physics done by the machines. Now, the question, if we go back in history, these things are always easier to answer. So if we would have looked in chemistry pre-1869, maybe one of the things that now we would say would come up with is if, the machine would have played Mendeleev's job in sense of giving us the periodic table. Now, in particle physics, also in hindsight, this could have been different. Could have been easily answered that if, we were in the 60s or 70s, something which was not on the horizon of people then was, for instance, the standard model or Gell-Mann's eightfold way. So these are kind of questions that, in retrospect, that would have been very interesting to discover with a machine. Now, but we're living in the 2020s, so we should, if we want to make such discoveries with machine, the question is, okay, which tools do we need to make such discoveries and to potentially ask this question? And this talk is about work in this kind of general scheme of trying to enable us to find mathematical structures to describe systems more efficiently. That's a very broad question. If you want to put this more into concrete perspective, various areas of theoretical physics, this ranges of applications from something like in dark matter phenomenology, understanding dark matter halos better, understanding strongly coupled systems better. But for the mathematical physics audience in this crowd, I think there are questions we could really ask about, understanding what is, say, for instance, the periodic table of Calabi-Yau manifolds. What are the patterns that we can actually see there to really understand what's going on there? But also to ask, questions about, say, detailed things about Calabi-Yau metrics, which we heard previously from Challenger, and later today we'll hear Fabian talking about our work in this direction. So in this talk, I want to focus on two things, namely to look at symmetries and dualities in the what theoretical physicists think about. So now, why do I care about them? It's basically they are really standard structures that we use to describe physical systems in a better way. So they make our life, very coarsely speaking, much easier. And that's what we want to do. So the exact topic I would like to talk about is first to talk about searching and utilizing symmetries. So this is work together with a PhD student here in Munich, Mark Sivery, which partially appeared already and partially is in progress. The second part is about using utilizing and searching for duality symmetries. This is work with Philip Betzler, who was also a PhD student in Munich. So let's start with the first part. This is about learning symmetries from the embedding a neural network is choosing for data. And so this is really the question we want to ask is, can we use some neural networks to detect symmetries that are underlying in the data? And so if you want to phrase it more accurately, say you have some function f of x, what are the symmetries leaving it invariant? And the idea that we have pursued in this paper is to see whether these standard kind of word embeddings that appear can actually be also useful to extract physical properties, like about information about the symmetries. So just to recap, what is this in the word embeddings is that when you're looking at language processing, if you're opening the box and look at some representation that is taken for certain words, what happens is that words of a similar meaning cluster together. So if you're thinking, for instance, about this equation, England minus London, you would find that this is gives you a rather similar value for these embeddings if you're looking at Paris minus France. And this is really obviously we know what is happening in terms of there. What's happening is putting things of similar meaning together. And that's what we want to utilize here to reveal physical structures, in particular to reveal symmetries of the data. And the spoiler is, yes, this can actually work. Good. So how does this work? So there's a two-step procedure. Basically, what we do is we first of all look at finding invariances that have invariances present. And what we do is we set up subclassification problem. So for instance, here, think of a standard Mexican hat potential you have, and you make it into a classification problem of what is the value of that potential. And then what we do is we analyze the position in the embedding layer, either directly or via some dimensional reduction. We go through various procedures. And then in a second step, once we've identified that there is some structure, we want to understand which structure this is, and basically which symmetry is generating them. So the problem there is then, okay, we are basically finding some point clouds which have some structure in them. And basically what we are looking for is identifying the generator that connects these point clouds. And okay, so let's look at the details a little bit, give you a bit of a flavor. So how do we find these invariances? So we're looking at a standard Higgs potential here. And as I said, we want to formulate this as a classification problem. So these values here obviously then correspond to the same class. And as you know, there's obviously your rotational symmetry around this. And then, okay, sample points from this class. And okay, you put this into a classification problem. And what we look at, okay, you can easily train. And what we look at is the embedding in the second to last layer and see what is happening. Now, one way of visualizing this is then to dimensionally reduce this. And what we apply here is, what I'm showing you here is a stochastic neighbor embedding in this space. And so if you then, in this simple example, look carefully, what you see is that you actually find exactly these two classes being separated, and this feature is persistent. Whereas for things where you have only one represented, this is only connected with this only has one connected component. Now, again, this then this is one of the things we started with, was also part of our motivation, is to understand actually these symmetries within complete intersection Calabi-Yaus. This was a challenge I was mentioning earlier in the talk, and this is really different types of symmetries that have been found for these Calabi-Yau manifolds. And what the data is here is essentially, as was already introduced, where essentially is some integer matrices. And what you have there are some certain discrete symmetries. So there are trivial ones in the sense of permutation, but there are also non-trivial moves in the sense of, for instance, these two kind of matrices are related by each other. Now, what we did here is we looked at, and we want to see whether our network can actually pick up on this and find this. And so this would be important, for instance, in the 4-dimensional case where you don't know all of the redundancies. Could you use a machine to handle it? But there's a warm-up. We're doing here the 3D case. Now, what we're putting in is not this representation, but what is seemed more suitable was to reformulate this in terms of some graph-like structure, and then to put the kind of local features in, so which kind of nodes you have, plus in addition the eigenvalues of the adjacency matrix. Now then, as a classification problem, what we are using is two topological numbers, which were also introduced nicely by Challenger, with H11 and H12. And then we let our our network classify things. That's a relatively standard feed-forward architecture. And then you can look at what are the distances in your embedding space. And this is a typically, okay, you pick one example and then you kind of look at where are the neighbors located. And you see that we find these kind of jumps here. Let's highlight this a little bit more about the differences. And so now you have to kind of come up with some recipe which tells you what you classify as the same Calabi-Yau manifold. A simple thing what we did is we just picked the highest kind of jump. So everything here we say, okay, this belongs to the same class. And then we see, oh, how accurate is some really crude measure like this. And what we see is that exactly this surprisingly works relatively well. Yeah, already to see this. This is actually a non-trivial exercise because there are multiple representatives with the same Hodge number. So there are multiple examples here which should be classified in the same way, which typically would be put on top of each other. But beyond that, the network is separating them, the ones that are belonging to each other. Now so we went also through some other exercises in the paper, but now so that seems to be working, that we can extract some useful information from the embedding. Now the next question is then okay, how can we find the generators? So what the problem is then, okay, so you have these things that are mapped together in one at one point, and if you're looking at it on the input space, you would have something which is, for instance, looking like such a point cloud. So this would be, for instance, if you're thinking about the input for the Higgs potential, you would have the rotated, so with different angles. So exactly something at a particular radius, but with different angles. And that's the kind of what you have. And from that, you want to use what generator is generating this. And so what we're left with is, trying to extract this from such a point cloud. And basically, what we're doing is, okay, in general, we're obviously in some higher dimension here. What we do is we pick a hyperplane and determine that generator. And we can, we can do this as a very easy regression problem. And then we do this a lot of times for different combinations. So we pick up every generation, and then we just do principal component analysis. And what you see is here basically that generator of the principal component analysis that's coming out. So if you're looking at these generators here, what you see is really the one that you're familiar with of SO2 very nicely. And you see that really the higher components, they're really not really generated. They're basically not there. So that's nice, and it's also like one should always look at how many points we need, and we can really go to relatively low number of points, and still, so this is just 20 points in this hyperplane, and still get some good picture. And if I look at this data, this really tells me, okay, yeah, this is clearly this generator. Now, okay, this was when I mentioned. Now, obviously, we have to go to higher dimensions and see that this is actually, we can extract non-trivial statements. So now here, basically the same thing is working as well. So we have some SON examples that we look at and subgroups thereof, right? So this is important because what happens if you don't really have the entire possible rotation group to see that you can pick up on this. And here's an example with SU2 where we do this. Now, this method is actually also then wider applicable. So we try to do something more, going beyond the realm of physics. So what we did is we did a simple exercise of generating rotated MNIST, and then see whether our method actually works. So to do this, what we did is we did a principal component analysis of these data sets. And what we actually showed is that we can really find clear identification of that.
I think we met already.
Yeah.
One second.
I just read your name. I don't really recall.
Sorry about this.
Yes, we met like I was in Bilbao.
Oh, okay.
I was in Bilbao to give a talk.
Sorry. This is the problem when you're hosting different meetings at the same time. So what happened is here that at MNIST, so we can actually find also the rotated generator for such a data set. So I think this is interesting if you want to apply something like this to different types of data sets. Now let's me come to another part of this talk, namely how to extract symmetries in a slightly different way. So this is about this problem of, when you're faced with trying to predict dynamics. So the goal here is to, given some input of the dynamics, to actually predict the dynamics most accurately. So this is work that these videos are from these works by Battaglia and collaborators. And what the goal is twofold. One is to give accurate predictions of the dynamics, and secondly, also to find the underlying physics model. And so what has been shown is that building in the physics bias to these neural networks does actually help. And so this is, appeared in 2019. This is basically trying to use our physics knowledge that we want to build in, instead of learning the future time steps in the sense of q dot, p dots, the time derivatives of your momenta and so on, as in Hamiltonian dynamics, you instead learn the Hamiltonian, and then by using auto differentiation, you can just learn the derivatives of that. So I showed that actually the predictions you're getting for very simple physical models like the two-body and so on, you can improve. So now these Hamiltonian neural networks, when you open the box, they do not necessarily learn the conserved quantities of the system. So there could be more constraints that can be used. In particular, you could learn about the symmetries of this problem and make sure that they are there. And so what we do in this work is to try to learn these, just basically, from the data again. And the language we use here is really going back to standard classical mechanics, where we are using, where we look at canonical transformations. So basically, if you're looking in Hamiltonian dynamics, what tells you that some quantity is conserved is that if you're looking at the Poisson bracket with the Hamiltonian, that this is vanishing. So what we are doing here is bringing these frameworks together of learning symmetries and the Hamiltonian. And so what we are doing is using these cyclic coordinates, using canonical transformations altogether. So what this is basically a two-step procedure, namely that we first transform our coordinates that we are given as an input to something which is obeying these symmetries. So for instance, what's happening is that if you choose appropriate coordinates, that they are constant. Yeah, so you're really just then looking at the movements in the hypersurface, and so for these you basically can throw away some of the coordinates. Yeah, that's what this is telling us. And then in the second step, what we're doing is we're learning that Hamiltonian. Now, to implement this, obviously have to modify our losses and to obey these kind of representations on in this latent space. Kind of give you a little bit of a flavor of what is happening here. So this is plotting some contours for these loss components for just a two-body problem. Just showing you this in terms of two-parameter language. So this is the underlying model, and here are contour lines of the respective loss. So these are losses here from the standard Hamiltonian neural network Cs. So this is basically looking at how far you are off if you're changing the mass parameter. Right? That's showing you this. But now what happens when we add this additional loss components is that we are adding that we're giving something biasing to that something which is even going to the closer direction. So this, like, you have these additional loss components which can constrain your function even more. Now then we run a couple of experiments, again using very similar things as done in this Hamiltonian neural network paper. And we can see some mild improvement comparing to the Hamiltonian neural networks. However, one also very interesting subject is then to ask what are the conserved quantities that we actually do find. And when we look at open the box again, what we see when we fit with some polynomials is exactly in this two-body case, where we know it's the momentum, the overall momentum that is conserved, and the perpendicular angular momentum. And actually our system is picking up this angular momentum. Yeah, so this is really encouraging that without telling it, it actually finds the conserved quantity that we are after. And so I think it's actually quite an interesting direction to build in as many physical constraints as possible, I think. And clearly we are just playing with very simple examples for now, and that's where we are improving on at the moment. We've run a couple more experiments where we also see minor improvements yet. So for instance, we look at standard things like a pendulum, but also some real data and the three-body problem. Now, let me come to the final part of this talk, where we're switching gears a little bit. Namely, we're looking for different types of mathematical structures, and we so-called dualities. So they are really, a very interesting tool in physics, and depending on which area you're specializing on, it comes in various shapes. But this is really good if you're coming from more computer science or mathematical perspective, is to look for a very good way to determine correlators. Yeah, if you're interested about the some correlation functions of your system, it's a very good way to determine this for instance, for strongly coupled systems. And what is the essence of this is that we basically have two descriptions of the same system, whereas one description is at very much strong coupling. The other one is governed by some different perturbative expansion, where it is at relatively weak coupling. So with this, one can really access different regions where classical solutions dominate. And so the question is, this is like such a deep topic in physics. The question was, when we wanted to ask, okay, can we make use of these different representations? And actually, when preparing these slides, came across when we Lars and Sanja made this nice excursion. And when you look at this kind of gate for this temple, well, it's actually also reminds us of it. Has something to do with dualities there. So there's this. If you look at the sign here of this at this temple, you would see that this is called the Dharma door of non-duality. So somehow, let's bring this connection to where this workshop is at least held virtually. Now, there's concrete applications in physics is if you want to look at, for instance, things like holography, or if you're interested in heavy ion physics, if you're interested in transport coefficients for Clark-Gluon plasma. So you can really compare these go through some exercise to comparing this with lattice techniques, so standard other techniques to determining such transport coefficients. And nice thing is that ADS-CFT, or the duality prescription, is actually better. So it gives you better results. And there it actually boils down to doing some metric perturbation in some gravitational background. So the question we want to ask is, can we make this picture of actually useful in practice? So can we connect these kind of things with some standard data questions? Now, the essence is, yes, we can do this, and for this we went to some physics examples where we see dualities. And the prime example when you think about dualities is probably the 2D Ising model, where we have standard high-low temperature duality. And in this context, one question you can ask is, what happens if you're just interested in getting some samples? You have some samples and you want to determine which temperature does this belong to. If you're looking at just the distribution, if you're forming it in normal coordinates, you are at low temperatures. And I'm plotting here just a two-dimensional plot of the energy and the magnetization. And you see that they actually very much clump together. Whereas you're thinking of it in the high temperature picture, if you're looking at the samples, they're very well spread across. So if you're doing a simple classification exercise on this, actually doing it on the data on the high temperature is outperforming the low temperature representation very much. Now, the question is, okay, so how can we, then if we know that it is good for classification, how can we find such good representations automatically? And so we went even further away than just the Ising model. And so the simplest example of thinking about dualities is thinking about a Fourier transformation. And so we did a very simple exercise. So consider the following toy setup. You have a signal in momentum space, which is just in one bin, and you put some noise on the topic. Now you want to find whether there's a signal or whether there's no signal. So no signal, you just have noise. Now, if you're asking this question in position space, you can't really tell any difference. However, if you ask this in momentum space, you can see a difference. Everybody can see this by eye. Now, the question is then, okay, how well does our neural network do? Obviously, if we put the signal strength low enough, so at some point it will not pick it up. If we use a standard network, not don't train for completely excessive things. What we'll see is we start somewhere at some random configuration and we converge to some local minimum, but we never really find a really good representation. Now, although we know that even already one single hidden layer, one standard linear transformation can actually learn this transformation in principle. So these beneficial representations are not generally adapted. However, the question is, okay, can we find nevertheless, tweak our system a little bit such that it adapts these good representations automatically? And the answer is yes. And the way we did this is basically by asking it to separate the position of something which has noise versus something which no noise in the latent space, or in some deeper layer. And what we then see is obviously an improvement in the performance. But interestingly, now this kind of separation also we can look at what it is doing. And effectively, you can ask, okay, does this correspond to something what you would imagine from using a discrete Fourier transformation? And it becomes relatively close to this. Obviously, you'll have some certain tilts in different dimensions a little bit, but it's picking us up some linear combinations. But overall, this is really a very nice, very close structure to discrete Fourier transformation that we see. Now, then we went on to do this a little bit more in terms of different systems. So here's this question for a 1D Ising model, where again we can ask a question about, and this, a harder question is basically to figure out whether some state is metastable or not. Still obviously something relatively simple as a system, but this question again with a similar strategy we can very much improve on. What we do here is the following strategy is basically we are using some kind of autoencoder structure, and what we demand is that on the latent dimension we are also still good on doing a very simple task, namely to classify energy. And what happens then is that actually in this latent dimension, once you open it up, and what you see is you will see that so what you see then is in this, so when you open this up, is that the intermediate variables very much represent again or can represent the dual variables. So what this is essentially, for this very simple example, a way of finding these interesting variables automatically. And so what's the perspective here? I think this is really, we're scratching somehow the surface a little bit, that we can get dual variables without knowing them. And this is, I think, very interesting, because we all know that dualities are very deep concepts in physics. So if you have an automatic tool for finding new dualities, I think this is very, very good. Again, also from the physics side is very interesting, because now this can actually, we have a tool which gives us better results for certain data questions we can ask, or we can apply it and try to enforce something like this in machine learning. And so that's, I think there's a lot of interesting potential. And so this brings me to the conclusions. So I'm also short on time. That I think we can, what I've tried to convey to you in this talk is that we can really find mathematical structures in a very unsupervised way. Yeah, and so the two things that I'm, was stressing there was one is to look at the embedding layer, what embeddings we find, and the second is to just purely look at the dynamics of the system, or just use information from the dynamics, and then see the mathematical structures emerge from there. So here the symmetries. And then, this is really interesting then, I think, to continue working on analytic formulae, so we can go and fit about this. And that gives us, in this case, for simple examples, the answers we've already known. Again, also in terms of these dualities, I think it's very interesting that we can enforce these representations in a neural network. And I think this is like us taking first steps. So we're gearing up really here for more substantial searches for new structures. But I hope to report on these things in the future a little bit more. So with that, I would like to thank you for your attention.
Oh, thank you very much, Sven. Should we just thank Sven